So while the presentation is going up, I'll just introduce myself. Thanks for having me here. It's been wonderful so far. My name is Amogh Dhamdhere. I'm a research scientist at, okay, there you go, it's up, at CADA, which is, we're a research group at the University of California, San Diego. It's working. This is, okay, yeah, that's better. Okay. So, yeah, we're a research group at the University of California, San Diego. We do a lot of internet measurements of topology and things like that. This is some recent work that we've been just starting to do with folks over at MIT. That's Stephen Bauer and David Clark, and a bunch of people at CADA. It's about measuring interdomain congestion on the internet. So just to set the stage, let me just give a little bit of background. Please bear with me through this one slide. So if you think about the interdomain internet, it consists of about 45,000 or so, roughly give and take, networks which are all independently and autonomously managed. We call them autonomous systems or ASs. And if you think about the relationships between these networks, there are broadly two types of relationships. So you have customer-provider relationships where the customer pays the provider, and you have settlement-free or peering relationships where usually no exchange of money takes place. Two networks agree to exchange traffic, usually for free. If you think about how this sort of ecosystem is organized, then at the very top of this sort of hierarchy, you have a bunch of tier 1 networks. These are large, usually international backbones. They're fully meshed with settlement-free peering links. If you go a little bit lower down the hierarchy, you have transit providers and who are sort of more regional in scope. And down at the very end of the hierarchy, you have these enterprise customers. These are networks that are mostly eyeballs. They're going to be receiving the traffic that comes from content providers. Content providers are interesting because they like to do a lot of settlement-free peering. They don't like to pay for their traffic. So they will have a lot of settlement-free peering links with other transit providers and destinations of their traffic. But they also need some transit links in order to get their traffic to where it needs to go. Settlement-free peering actually is interesting because it's sort of loosely based on this notion of balance of trade. So if two networks think that it's mutually beneficial for us to exchange traffic for free, let's go ahead and do that. And this works for the most part, but because of this sort of loosely based on balance of trade, it can lead to peering disputes. And this has happened quite a bit in the past. We would have these these large transit providers, and they would sort of stop agreeing on whether this relationship was still mutually beneficial to them or not. And one network would then depeer the other network. It would say, you're sending me too much traffic, this relationship is costing me too much, it's no longer mutually beneficial, we shouldn't be peers anymore, you should pay me. And that kind of thing. And usually this kind of thing would lead to a depeering, so there would be a disconnection between two networks, and when that kind of thing happens, single-homed customers of these networks can't reach each other. So there's actually sort of a partition in the internet. There's a long list of these disputes over the years, dating back to 1998. And the steady stream of these things sometimes make the news, sometimes they don't really do that. But more recently, if you look at, say, the last few years, we've seen these disputes more in the news, and that's because they actually have been between some of the largest content providers around. So that was some history, and this is more recent stuff. What we've been seeing is that peering disputes no longer seem to have this, no longer seem to lead to disconnections. They don't lead to depearings anymore, at least not visibly. But what seems to be happening is that peering disputes tend to manifest as performance degradation, and especially performance of high bandwidth applications such as streaming video, and particularly as seen from these large broadband access providers. When you have access providers with millions of subscribers and their videos are starting to buffer, these people get angry, and when people get angry, they go online and write blog posts, and they post in forums and so on, and they get, they can get pretty nasty. So this is a blog post or a forum post by this customer on Netflix, customer of Netflix using Verizon Fios. And he says he has a 35 Mbps down, 35 Mbps up, blazing fast internet connection. Why the heck does his Netflix still not work well? There are lots and lots of customers on Comcast, many millions of them. They get angry when Netflix starts behaving badly. And oftentimes these kind of posts take the tone that it has to be Comcast that's throttling my traffic. Why else would Comcast not work? Why else would Netflix not work? And everything else seems to be working perfectly fine. And when we have disputes between things like this, where you have content and you have access, you can't go too long without hearing the term network neutrality. And as luck would have it, actually, Verizon recently won a very significant decision on this exact issue of network neutrality. So, well, they were just asking for it, right? Now, they just completely got it from a lot of people on blogs who are saying Verizon is basically using their recent victory in network neutrality to completely wage a war on Netflix. They're throttling Netflix traffic, nothing works on Verizon. People went the next step. Some kind of tech-savvy people like us, they do a little bit of poking around and run a few experiments here and there. So some people said, okay, let's look at Netflix performance on Comcast and Verizon, and it doesn't seem to work very well. But when we run the same Netflix video through our corporate VPNs, voila, it's now working perfectly well. So our access provider is playing games with us, and they're probably throttling our Netflix traffic or something. So, you can keep going on and on about this. Verizon, of course, they have to deny it, and they release some very lengthy statements on their public policy kind of blog. They went into a lot of details about this. They're saying, look, people, this is not we're not doing anything with your Netflix traffic. What you think is this huge, big dispute about network neutrality and all of that is nothing of the sort. This isn't a story about Netflix or about Verizon. It's a simple peering dispute. This is a dispute between Verizon and Cogent. Cogent is a transit provider who most people have never even heard of, but apparently, well, not apparently, they do provide transit for Netflix. And Verizon says this is a simple old-fashioned peering dispute. The only thing is this peering dispute is not leading to a disconnection, it's leading to congested links. It's leading to traffic flowing over congested links. That's why your Netflix videos suffer so bad. Well, and Netflix seems to agree, actually. They say that Verizon is probably not doing anything bad with the video stream. It might be something else. So the problem is, the bottom line is that these kind of peering disputes have been happening a lot. They're between these large content providers, they're between access providers. Sometimes these intermediate transit providers are involved. And it looks like some content is clearly being carried over links that are insufficient to hold, to serve that content. One thing to note here is that congestion on transit links affects everybody. It doesn't only affect the two parties to the dispute, because say you have a transit provider who's running all its links hot. All the content that's being served by that transit provider is going to suffer. All the destinations, the eyeballs who are accessing that content are going to see poor performance. Now, even though this is all over the news these days, the problem is that to a large extent, data about the location of this kind of congestion and performance degradation is pretty sparse. It's very anecdotal. So you see emails on the nanog list every now and then saying, look, all this. I'm seeing congestion between level 3 and AT&T and so on, and they post some trace routes here and there, and that's pretty much it for the time being. So what we're trying to do here is this is a project that we've just started. The goal of this research project is really to characterize the extent of interdomain congestion and try to figure out how it may be affecting the applications that people actually care about and the kind of things that we actually do online. And so we have several goals, but these are the sort of the three main important goals of this work. The first is to develop methods to detect congestion on interdomain links and try to localize that the congestion to specific points in the topology. So if you take that to the next step, what we really want is a sort of map of where interdomain connections exist, who connects to who, where do they connect, and what kind of congestion state do those links carry? Are they congested or are they not? We hope that the data that comes out of this kind of study is going to improve give some transparency to all of this, and add some empirical grounding to this whole debate, which so far has just been sort of going along in anecdotes and hearsay. I should say at this point that this whole ecosystem is really complex. You can maybe detect which links are congested, but trying to infer why that's so, which network actors are actually responsible, or what kind of incentives they have for doing so, it can make your mind spin. I mean, that's not really the goal at this point. It's not the focus, not at this point at least. And finally, I will give a disclaimer. This is very early work. We're still developing the sort of methods that we are using here. We are seeking feedback and validation like all the time about this work. So, if we want to try to measure congestion on links, the sort of basic assumption that we're going to run with throughout this talk at least, is that when links become congested, queues fill up. And when the queues fill up, the network delay for paths that are traversing that link increase, and the loss rate is also going to increase. And the amount by which the delay actually increases should be related to the queue size of the congested router. So let's take a pretty, a toy example here and say this is the traffic pattern that is seen at a given network location. This is a certain link. It may or may not be an interdomain link. Let's assume that the load follows this diurnal pattern, which it usually does. I mean, load during peak hours, I mean, this is when people are online and they're watching their movies and so on. It's the highest. And when people go to sleep, load is the lowest. So this is the sort of diurnal pattern that you expect and you do see in most cases. Let's take 3 different provisioning scenarios. Suppose in case A, we have a link that's provisioned so that the capacity is actually more than the maximum load that's ever offered to it. What sort of delay pattern are we going to see through that link if we plot the delay over time for paths traversing that link? You should see a fairly flat line. It's basically just your propagation delay, very little queuing, except for maybe some random noise here and there, but for the most part you should see a nice flat line. Suppose you have provisioning scenario B, where the link is provisioned such that it's just slightly less than the maximum load that's actually offered to it. In this case, what you're going to see is the delay is going to be flat for the most part, but you'll have little spikes that pretty much correspond to the peak slots every day. So, and finally, if you have a link that's significantly under-provisioned, so this is provisioning scenario C, where for a large amount of time during the day, it's congested. What you might see in this case is a waveform that looks like this. It's flat when there is no congestion. When the load starts to build, the queue starts to build, but then the queue reaches the limit. It reaches the queue size, and then it can't increase anymore, so you'll see this sort of chopped off waveform at the top. An increase, and then it'll be flat for the duration of your peak period. And that's the sort of thing you'll expect and try to detect in this work. So given this sort of method, it's fairly straightforward to devise something simple that might actually detect something like this, right? So we have a vantage point where we can send and receive probes. We have a network link that we are targeting, and that means we know the interfaces of the 2 border routers that are on that link. We call the one that's closer to the VP the near end, and the other one the far end of the link. So suppose from this border router we now issued probes towards a destination that we know is behind that link. We issued probes TTL limited such that the first probe expires at the near end of the link. So we basically, in this toy example, would set the TTL to 2 of the outgoing packet and get a response back. So we have an RTT to the near end of the link. Similarly, we have an RTT to the far end of the link by setting the TTL to 3, again TTL limited probes to the far end. And we keep doing this, and we just repeat this whole thing to obtain a time series and see what the time series looks like, and that's why we sort of call this thing time series ping. And hopefully, if our assumption earlier was correct, we should be able to go and look at the resulting time series, map it back to one of the kinds of waveforms we expect to see, and say that whether the link is congested, if it's slightly congested, or it's persistently congested. So we try to experiment with this. We have a Vantage Point. So these are these CADA archipelago monitors. These are, at this point in time, these are little Raspberry Pis that we give to people to deploy at their homes or elsewhere. And they basically can, we control them, so we can do all kinds of measurements with them. So this is at a large residential broadband provider on the East Coast, in Boston, actually. And using some initial sweep of trace routes on this monitor, we were able to identify interesting links that we actually wanted to measure for congestion. And we employed this time series ping on that box, targeting this specific link, and looked at this waveform over the course of 1 week. And basically what we're seeing is the red line here is the RTT to the near end of the link, and the green line is actually the RTT to the far end of the link. And each of these is 1 day. So basically, even visually, it's very easy to see here that there is a clear diurnal trend in the RTT towards the far end of the link. The green line clearly has that step sort of waveform that we expected to see for congested links. And there's no trend in the RTT to the near end of the link. So this is pretty, this is compelling. This looks like this link is actually pretty congested. A few more tidbits which seem are quite intuitive when you think about them. The length of the congested period is longer on weekends. This is when people are at home, they're watching more movies online. In this case, the length of this period was longer on Monday, and it happened to be Veterans Day that day. So again, people at home watching more movies, more congestion. To sort of drive this proof of concept further, to make sure that we are actually measuring what we think we're measuring, whether this is really congestion and not some kind of game someone is playing, we also enable some loss measurements from that same monitor to the same target link. What we do is we just simply ping the far end of the link frequently, once every second for a while. We only did that for a week to not annoy too many people, and then we turned it off. But it basically confirms what you see in these diurnal plots. As the delay increases, the loss rate is increasing. The delay stops increasing because the queue is now full, but the loss rate keeps increasing because the load is increasing actually. So this is pretty neat. I mean, it gives us some confidence that we can actually do this kind of thing. But of course, I mean, with this any of this kind of measurement, there's a ton of challenges that we have to overcome. I think the first one, the most important one is really about the reverse path. So what we're doing here is sending TTL limited probes to the near end of the link and the far end of the link. Now we know the forward part to the near and the far end, but we do not know the reverse path. So it may very well happen that the reverse path from the far end of the link back to a vantage point doesn't cross the link we're actually targeting. It might be connected to a different router, it might be connected to a different parallel link on the same router, it might be connected to a router in a completely different AS. And just using these sort of TTL limited probes, we don't really have a way of knowing that. Several methods that we are actually trying to employ to get around this issue is reverse trace route. First of all, we might do a trace route from either the destination or the border router itself back to us. This is the reverse trace route method that came out of UW. We might try the IP record route option. What this can do is basically, if the link that we are targeting is less than 9 hops away from our vantage point, we can get the reverse path back to us if the routers actually honor the record route option. We can try the timestamp option, which is basically sending probes with soliciting timestamps from the near and the far end of the router. And actually we would do the near and the far and the near again, and try to see if, first of all, if the link is crossed on the reverse path, and try to see which direction the congestion actually is. So there's still lots of things to be sort of done here to make that solid. Another challenge is actually that a lot of interdomain connections that we see consist of many parallel links. So there's 2 routers we can do alias resolution and things like that and figure out that these are actually the same router, but they're connected by many, many parallel links. We've seen as many as 16 in some cases between two networks, between two routers interconnecting two networks. Now, one of the issues that is simply that you might traverse one link on the forward path and one of the other ones on the reverse path, and one might be congested, one may not. So there's some things like, should we be probing all the parallel links, or should we, is it safe to assume that if you have parallel links, all of them are sort of load balancing works, and all of them are equally loaded, and so you can probe only a representative link. So that's another challenge. Finally, and this may not actually seem like a challenge, but it's actually non-trivial to identify which link is the interdomain link, given border routers and the way things are named. So in this little toy example, we have routers R1, R2, R3. Each of them have address space. These are interfaces, and this means that the interface is named out of A's address space, ASA. This is named out of B's address space, and this one is named out of B's address space. So what's happening here actually is that this interdomain link is actually between router A and B. It's actually that this /30 is all named out of A's address space, and it could as well have been named out of B's, but that's just the way they chose to configure the link. So suppose we did a trace route now from left to right. The interfaces we would likely to be seeing are A1, A5, and B3. So if you just went by a simple naive IP to AS kind of mapping, what you would think is that the interdomain hop happens here, which is between R2 and R3, which is actually one link too late. So it could really be any of these two hops. This one is a little bit easier to get around. I mean, we could just simply probe all three IPs, right, and just be safe about it. One of these two hops has to be the interdomain link, so that's all right. Otherwise, we could look at reverse DNS kind of things to try to figure out where the AS boundary is actually changing. So various other challenges. I mean, interdomain links come and go. This whole thing is really sort of fluid. It always seems like we're trying to measure something that's changing all the time. So we do need to be adapting to routed paths and topologies that change over time. It's not trivial to determine which direction the congestion is in, like I already said. Finally, I mean, ICMP responses may be queued differently. People may be aware that we are actually, we or someone else is actually trying to measure congestion in this way. They might be actually trying to prevent us from doing so. Finally, we have, a huge number of interdomain links, many hundreds of thousands of them. This will generate mountains of data if we actually manage to get this running. We need serious sort of methodological ways to pour through all this data to find interesting cases. So what we've been doing is sort of the current thought in how we design the system is we have these ARC boxes. We have about 70 or so of them. These, like I said, at this point are basically these Raspberry Pis that we hand out to people and they go and deploy them. These boxes are continuously probing the entire routed space, and they're trying to find interdomain links that we can then ping. Then we enable this time series ping kind of measurements that I mentioned previously on each of these interdomain links. Now we need to do some optimization to make sure that we're not doing a whole lot of redundant probing. So there's some algorithms that we developed to just basically optimize the set of interfaces to probe. So we cover everything, and we don't just send out too many probes and annoy people. We are making the system adaptive, so this thing is going to continuously update which set of links to probe based on the current routing state. And finally, we've been implementing level shift detection on these time series and playing with frequency domain analysis to actually figure out diurnal patterns and then find interesting links in the data. So some quick examples, a few more examples of what we've been seeing, and I've since this is pretty early work, I mean, I've been anonymizing all the network names involved. So this is again from one of our residential ARC monitors. this is a link between a very large access network and a transit network that's actually serving a very popular video streaming service. And this link has been, ever since we started probing it a few months ago, this link has been persistently congested. This is, at this point, it looks like it's only a few hours of the day when it's not congested. All the other times it is pretty much full. This is, again, a large residential broadband provider. And if you go online and dig up complaints from people who've been experiencing very poor performance for a particular video sharing website, and again lots of conjectures about why this is so, but this seems to say actually why this is so. It's basically the peering link from that access provider to that video sharing website is showing pretty clear signs of congestion almost every day during the peak hour, several hours a day. I should say, of course, that it's an important part of this study is to find and sort of confirm links that are not congested. And I should say that most links that we have measured so far do not appear to be congested. I've just posted some of the interesting ones that did appear congested, but most of them are not. And here is an example. I thought I should pull out a link from that I see with Yahoo, so because I'm here. So this is a peering link, and I can actually de-anonymize this. So in the hopes of getting confirmation and ground truth, that's the only reason. Anyway, so this is we have a box in Cox Communications, and this is one of the several peering links we found with Yahoo. This is the AS10310, the big Yahoo AS, I believe. And this appears, it does this amount of noise because I've zoomed in pretty closely on this range, but for the most part it's flat. You don't really see diurnal, level shifts kind of thing. Most of the noise in this thing can be attributed to sort of slow ICMP behavior on routers. So I'll finish this talk by saying a little bit about whether we have the data and whether we have any way of saying something about what happened in the past with congestion trends, because these measurements are something we started very, very recently, a few months ago. What happened, say, last year or years before that? So if you think about it, the time series ping method is very similar to running frequent trace routes. It's actually exactly the same thing, but just TTL limited to the same exact 2 hops. But why couldn't we just run frequent trace routes all the time, and you'd get actually congestion kind of signals for every link on the path. As luck would have it, at CADA we do a metric ton of trace routes, and we've been doing this for 10 years or so from these set of ARC monitors, which continuously probe all the /24 prefixes in the routed internet. They don't do this to measure congestion, they do this to measure topology. And so we also have these historical reverse DNS lookups, alias resolution, lots and lots of stuff that was collected not for the purpose of measuring congestion. But, I mean, maybe, just maybe, we have something in there that can tell us something about historical congestion patterns. So we started pouring into this data, and it actually turns out to be incredibly messy, as you would expect, because things change over the years, lots of things come and go. We have gaps in our data. And because these measurements were not conducted for the purpose of measuring congestion, we are not guaranteed to be seeing links consistently and regularly and at a high enough frequency that we can actually measure this. But it so happens that because of the way routing works, and a lot of even if we just probe the entire routed space, a lot of the packets are going to traverse a few links on the interconnecting on the host network. So what happens actually is that for a few high-profile links, we actually have very good data, and they're sampled consistently and they're sampled frequently enough for us to do some historical measurements. So just one example, again, this very large broadband access provider, where we have a box, and we've had this box for several years now, actually. This broadband access provider is connected to 3 transit providers, A, B, and C. Each of these transit providers was, at some time or the other, perhaps not all at the same time, serving video from a very popular video streaming website. And in our data, we can actually see all of these 3 links of the access provider with this transit provider very frequently and very consistently, enough to look at congestion patterns. So here is what we see of the first half of 2013 for the access provider to one of the 3 transit providers. For this entire duration, this transit provider wasn't actually carrying traffic from the video service, and this is something, you can find this in the news. There is a little bit of congestion, right? I mean, there are times when, some days where every day there's a little bit of a spike. April, I don't know what happened here because there seems to be something more going on. But you can say there's slight congestion pretty much every day of in some months. But things changed rather dramatically when, according to news reports, this transit provider acquired the traffic from the large video streaming service. And this was, according to news reports, it was around here somewhere. And now you can see pretty much every day, many hours of the day, this link is pretty heavily congested. This goes on, this goes on. I mean, these are gaps in our data every now and then. But now you come down to the point of November and December 2013. It's at this point, again, the time when this link is not congested is pretty small. It's like 6 hours. It's congested for 18 hours a day. And this is the link between this large broadband access provider and transit provider. Finally, I'll end with this one graph. So again, for that same scenario, transit provider A, B, and C, what we plotted here is for many months during the 2013 and 14, how many hours during the day we believed that this link was congested, as indicated by our sort of level shifting. So the blue dots, transit provider B, it actually had traffic from the video service around this time. I'm sorry, this is provider C, which had the traffic, and then it lost it. It lost the traffic, so the congestion on those links went to pretty much 0. And then what happened is, actually, because they had these big links that were carrying a lot of video traffic, and then they lost all that traffic, they actually moved that capacity elsewhere. So they decreased capacity on the links which were not congested, and they became congested again a little bit. Around this time, again, is July 2013, is when transit provider A acquired the large video streaming service. You can see the clear jump in the amount of congestion every day. It's at 8, 10, 12 hours, and now it's approaching the point where it's ridiculous, right? It's like 18 hours a day at points. So that's it. I mean, the end goal of this work, and I should say again that this is very, very early stuff, is to have a lightweight and easily deployed method that we can push out to these arc boxes that we already have. Try to find congestion patterns wherever they exist. We're of course looking for validation from operators and people who know the state of links. And we are very interested in feedback about what kind of data should we be collecting, how much should we be keeping, and so on. Improvements to the method, places where the method would fail, what else could we do differently, and so on. Finally, this is the standard KDA plug. We're always looking for more vantage points. At this point, it's very easy. It's a Raspberry Pi. You deploy it in your house. If you're at an interesting residential broadband provider, please let me know, and we can talk about it. That's pretty much it, and I'm happy to take questions. Yeah.
Hi.
Yeah. That's fine.
I didn't need a mic. Hi. So, first thing, I would love to host an article answer.
Sure.
Second thing, obviously, Write have their Atlas platform. Have you ever considered piggybacking off of that? Because they have over 4,100 probes running actively right now, and I believe they have the facility to self-define metrics, and there's a whole API to do interesting stuff. And there's a lot of scope there to talking with them.
Yes, so we would love to give you an Raspberry Pi to host, and yes, we've talked about using the Atlas Pro. So this is that's sort of part of this sort of long-term project. The Atlas, the RIPE Atlas probes, you're right, they do support user-defined measurements, but we do want to, push these, get these measurements on our own, controlled boxes to a point where we can then deploy them to the Atlas probes. And the Atlas things also have some limits in terms of, they have the concept of measurement credits. So there's only a limited amount of probing that you can do from there. So we really want to get this method optimized to the point where we can say, do the minimum number of probes from a given Atlas node. But yes, that's definitely not radar. Yeah, and we do work with RIPE NCC and so on.
Yeah,
so
sure.
yeah.
I was actually going to ask an extension to that, Tony. So what is the minimum number of tests that you would need to run to get a good idea of whether congestion is happening?
That's something we haven't, we haven't looked too deeply into that yet. I mean, we've been doing this every 5 minutes at the moment. The time series ping is every 5 minutes, and we find that an RTT sample every 5 minutes gives us a decent enough signal. For some of the arc traces, the historical thing that I showed, we actually sample some of the links much more frequently than 5 minutes. So we get that very much more sharply defined waveform. But with sort of a granularity of 5 minutes, we're able to do pretty low rate probing from our arc box. So this is like 50 packets per second. These are small packets. So at this point, this is very, very low overhead. And 5 minutes, every 5 minutes seems to give us a decent enough resolution.
That's true, but if we want to extend this to another third-party measurement service, it might not be possible for us to do it every 5 minutes.
Sure. So that's where we are actually, the folks at MIT have been looking at this frequency domain stuff. So they're actually, sampling the data to see what sort of lower resolution data would be good and still give us this diurnal waveform kind of thing. Yeah, we're still looking into that.
So latency seems like a somewhat odd indicator, unless to go back to your graph where you had loss. So there are basically two types of applications. Ones that are very latency bound. So when we talk about things like earlier today about RDT limited systems, okay, great, we have a measure of what congestion we have. But for the type of application that you're specifically targeting, things like video, you're probably much more bandwidth limited, right? And while it takes relatively little traffic to saturate out the, effectively the latency to sort of a flat top type curve for these type of environments. So my question is, what do you do to sort of really estimate available bandwidth? I mean, it would seem like if you look at your loss curve, it's clearly not a flat top, right? The available bandwidth at the beginning of your flat top is very different than, I can't tell, the sort of latter half of the middle.
Right. That's a great point. And actually, I didn't say much about that here, but complementing this sort of active probing, we've been working with folks at Google who are developing this tool, this bandwidth throughput measurement tool, basically. And our hope is actually to use so it will be a sort of client-server tool. It does throughput tests, and you do trace routes in both directions and sort of do tomography to try to figure out where the congestion might be. And I didn't say that, but that's sort of what we're thinking of as a complement to just delay and loss-based tests.
I have a very similar point to what Skinny mentioned. So I was wondering if instead of pinging, if you fetch videos frequently and look at TCP behavior, how many retransmissions, and because TCP is very aggressive in sampling losses compared to what ping does. Look at congestion behavior, look at retransmissions, and also look at what is the phase share of the TCP throughput that you get for that video.
Right.
I think that probably will give you even worse statistics than what you're seeing right now.
Worse in what sense?
In terms of the sampling behavior of TCP is very aggressive, right? So it tries to sample losses. You will see a higher loss rate, higher retransmission rate. and
Right.
lower congestion windows than you would expect, and probably achievable throughput will be much lower than.
Yeah. So yeah, I mean, I didn't say anything about throughput at this point, but that's really the focus of this other thing that we're doing with Google. And yeah, I mean, we hope that these things can be sort of complementary, because we see a increase in the latency, but what does this mean for video quality? I mean, we don't know. Maybe the video quality went down and no one noticed, right? Maybe the user didn't notice. So yeah, that's sort of in the works.
Thank you.